Welcome back to some more geometry. Today we are talking about writing proofs. All right, so to write proofs, you got to know a couple of things. So real quick, when we talked about proofs, back when we were talking about deductive reasoning, remember deductive uses facts. So deductive use certain things. It talked about definitions, so use definitions. There you go. It used, what was the other thing it used? It used theorems. It used, what was the other thing? Definitions, theorems, postulates. And what was the last thing? Terms. Undefined terms, or just terms in general. Certain terms. All right, so today we're going to look at the postulate side of this. So postulates, again, are statements that we accept as true without any proof. So, for example, the current president of the United States, we know who he is. We don't need to be at the White House to know who he is or see him every day. Okay, the professional basketball team in Oklahoma City, that's also the current, we take that as true without having any proof. We don't go to Oklahoma City and see. I mean, I go quite a bit, but other people don't. But I've never been to Toronto to see the Raptors, but I know that they're there. So we take it as proof, true without any kind of proof. All right. So there is 7 postulates that we will speak about in this section. So let's look at the first 2. The first 2, all these postulates are based off 3 things: points, lines, and planes, and their relation to each other. So first one says that through any 2 points, there's exactly 1 line. So, I said any 2 points. Any 2 points are exactly 1 line. So these 2 points will always create exactly 1 line. Could I have more points? Yes, but I only need 2 points to create 1 line. And then 3.2 says through any 3 non-collinear points. So that's the key word here, non-collinear. They form exactly 1 plane. Now imagine if you had 3 points in a line. You can have multiple planes go through that. You can have planes that go this way, one that's slanted through it. The diagonal, it's diagonally. You can have multiple planes go through that. But when they're non-collinear, meaning not in the same line, they can only form 1 plane that connects them all. All right. These next 2 right here, 3.3 and 3.4, they're the converse of the last one. As you see this last one, we went from points, 2 points equal 1 line, 3 points is 1 plane. Well, vice versa. If I know I have a line, I have to have at least 2 points for that line. And I know I have a plane, the plane has at least 3 non-collinear points. So this time, now the line is creating the points. Not creating the points, but the line is defining the points, and the plane is defining the points versus the amount of points defining the shape. 2 points, 1 line, 3 non-collinear, 1 plane. All right. 3.5 states that if 2 points, so 2 points, for example here, A and B, are on a plane, then the line that goes through those 2 points is also on that plane. Previously, we saw how you can draw a line that goes through a plane and it only intersects at 1 point, which that happens. But if you have 2 points on there, then that line also is on that same surface. All right, the last 2 we're going to talk about here is 3.6 and 3.7. Let's talk about the intersection. So when 2 lines intersect, they intersect at exactly 1 point. So they kind of form a point. Because right now, by me having just these little arrows on the end, I say, hey, there's a bunch of points that go through there. But when they intersect, they have that 1 point in common. That's why we say the intersection is exactly 1 point. Same thing with planes. When 2 planes intersect, so these are kind of going through each other, they create a line almost like the edge of 2 walls. When 2 walls meet, they form 1 edge. That edge right there is a line. Because theoretically speaking, planes don't have an ending. They have no boundary. They go forever in every direction that they are kind of created, if that makes sense. But we draw the rectangle to kind of give it some sort of tangible image that we can see. So these 2 planes intersected. They intersected at this little corner right here, forming this line. All right. Now these 7 postulates will be used throughout the homework and on the test, as well as the next slide. So let's look at this next slide. So here, we're going to justify our answers as always, sometimes, or never true. Okay. So for example, A right here says the intersection of three planes is a line. Is that always true, sometimes true, or never true? If you had a guess, as we did in class, you would say sometimes. The reason you say sometimes is could it? Of course it can. For example, let's say we have this right here. We already have two planes. And let's imagine there's another one that goes right through this, right at that same intersection right there. Right there it goes. So it goes through that spot right there. That spot as well. So yeah, can it go through where they only have one line? Yeah. But is that the only way it can happen? No, that's not the only way it can happen. So that's why it's a sometimes. So and you'll use that theorem as your example, as your proof here to justify it. So you say, if two planes intersect, then they intersect at one line, or their intersection is one line. Yeah. Okay, so sometimes. Next one, line R contains only point P. So line R only has one point P. That's a never. Because as we saw earlier up here, a line contains at least 2 points. So that'd be your justification. A line contains at least 2 points. 2 points. So there you go. Last one, through line H and K. So, and it's assumed that they are intersecting because I mistyped that. Through intersecting line H and K, there's exactly 1 point. That is an always. Always, like we saw in 3-6 here. Two lines intersect, their intersection is exactly 1 point. So two lines intersect at 1 point. So this is a couple problems in the homework will be just like this. So you'll have to go ahead and write sometimes, always, and never in the justification for that. All right, so let's get into the actual proof part. So as you're taking notes, I told you don't worry about writing these two. This is just there so we can kind of discuss it over. So again, our proofs are just arguments. Okay, they're arguments in which we give statements, and then we also have supportive statements that support our answer to be true. Okay, as it says right here, the supportive statement can include undefined terms. So like, hey, a triangle, a circle, they're what they represent, they're considered undefined terms because you really can't make a true triangle. Definitions that we saw earlier, postulates and theorems. We're really looking at that. In the next couple of sections, we'll talk a lot more about theorems, but right now we're just talking about postulates. Now, two-column proofs is the most popular way to do these, as we'll do two of them here in a bit, but we'll also talk about float proof here soon as well. But this you did have to write. So the definition of congruence. So the definition of congruence is just a definition that lets you manipulate your problem. So in the grand scheme of definition of congruence, all it is saying is that anything that is equal is also congruent. So if I know that they are equal, then I can say they're congruent. And vice versa, if I know things are congruent, I can go ahead and say they're equal as well. And as we'll see here in a bit, how we use that in the two-column proof. So let's look at this problem right here. Here we say that Q is the midpoint of PR. So this little Q point splits PR in half because that's what midpoints do. So because I know Q is the midpoint PR, then I can go ahead and make the assumption that PQ has to be equal to QR because by definition of midpoint, I'm allowed to say that those individual parts are congruent to each other. So because I know that the individual parts are equal to each other, then I can go and say that the individual parts are congruent to each other by the one that we just wrote down, the definition of congruence. And you can shorthand congruence just CONG. That just means definition of congruence. Kind of helps you as much as you're going to write, kind of write a little less right here. So hopefully that kind of helps right there. Let's kind of see how definition of congruence works. Now this definition of midpoint, let's talk a little bit more about that because this is the first time we have completely actually talked about it. We've seen midpoints, we worked with midpoints, we assumed midpoints, but what does midpoint do exactly? So it's twofold. Okay, midpoints, if you know something is the midpoint, then you can assume that individual parts are congruent. But the other way around, it also works the other way around. If I didn't know this was true, but somehow I proved that PQ and Q are congruent, then I can then go ahead and state then Q has to be the midpoint because the two individual segments are congruent to each other, forming that midpoint, that this has to be the halfway point. So midpoint works two ways, all right? All right, so this problem right here, I had you take some time, work on it with the people around you. So let's kind of work on this together. First, let's look at our given information. We're going to do the given in blue. So given information is the B is the midpoint. So we can go ahead and state eventually that those two parts are congruent, and we will do that here in a bit. And we know C is a midpoint, so we can say these two parts are congruent. They also tell us that AB, right here, A to B, is congruent to CE. That's all given information right there. Okay, the goal, I'm going to do this in red, is to state that BC right here is congruent to DC right there. That's the goal, to say those two individual parts are congruent to each other, which hopefully we'll be able to do that. All right, so let's check this out. Switch, we'll keep it in red right here. So given information, B is the midpoint of AC, and C is the midpoint of DE. Okay, that's given. So by definition of midpoint, I can go ahead and say that AB is equal to BC, because that's kind of the implied information from that. And we put on the same one, so it's semicolon, DC is equal to CE. All right, that's what definition of midpoint does. So let's just go ahead and take that information that we knew and then create something from it. Now, AB is equal to CE. That was given information. That's what they wrote given. But let's look at this. So somehow we're going to eventually turn this third statement into this fourth statement, and that fourth statement will lead us ultimately to our final answer, BC equal to DC. So let's look at this. So in here we say AB is equal to BC, DC equals to CE, and we also know that AB is equal to CE. So it doesn't matter which one you do first, but since I know that AB is equal to CE, and CE has to be equal to something else, kind of doing the whole law of syllogism, AB here is also equal to DC. Yeah, see, and we wanted that in that spot. Now, what did we just do? We changed CE with DC. By changing it, we did what was called substitution. So substitution. I'm going to shorthand it, so you have to write it out every single time, but substitution. All right. And then what did they do one more time? They substituted AB with BC. So that's another substitution. So you can have the same reason happen twice. It's just we wrote it do different things. You can see individually is substituted here first and then substituted over here second. So that's how this problem worked. All right, let's look at our last one. So we talked about float proofs. I mentioned it, but let's kind of talk a little bit more. Float proofs is just a way to do proofs. Okay, it just looks in a different format. So here we have a box. Inside the box is what we call our statement, and then outside the box is our reasoning for that statement, why we're allowed to say that. And then you kind of see the progression that this follows, the argument, and how we ultimately get to the final answer. So in class, we said, all right, I filled in this middle part because this is the part where it does do it a little different than we've done the last two. So let's see what happens. So here, previously we said P is the midpoint of JK. So we will say JP is equal to PK, but they didn't do that. That's the second thing right here. But they did definition of congruence. That means previously, instead of saying they're equal, they said JP is congruent to PK, and that's very much allowed. That could happen as well. So JP is congruent to PK. That's our definition of midpoint. And you always write it underneath the box, midpoint. Midpoint. There you go. And then they switch the congruent to equal. That's definition congruence. Like, all right, so we got the right parts. Now remember, things have to be equal to be able to manipulate them, to change them, to switch them out. So as we're going to do here. So the goal, as you can see, the next box, they already started subtracting and started working the problem out. But wait, where did the problem come from? Well, since we said, or we look at the graph here, JP also equals X and PK also equals 5X minus 8. So they substituted. They said X equals 5X minus 8. That's our substitution. We did that right there. And then from there, we'll go ahead and you see the problem, they went ahead and subtracted 5x on both sides. Now, 5x, as it's subtracted on both sides, they're showing you that they're doing the work, and then they go ahead and actually do the work. So they say substitution. Previously, this is the first time I've seen the substitution. We call that substitution, but they can also call that simplify. They simplify. This exact same book, but the previous chapter, they use simplify instead of substitute. So it's interchangeable, apparently. And then from there, we would have divided. So they show you the division, that's what the division, but the actual final answer will be this. Because remember, the thing we're trying to prove will go in that final box, but if you look at the work, they actually just went ahead and divided by the -4. So they, according to their language, they substituted, or like we said before, we just simplify. Simplify. Hopefully that helps, and that's all I got for you. If you have any questions, feel free to ask, leave comments, or get to me. All right. Bye.